Hello, everyone. Welcome to this talk. So I am Matteo Salvarezza from Wolfram Research, and I'm presenting together with Maria and Tushita. In this talk, we will demonstrate a few conversion pipelines of neural networks to and from between the Wolfram language and external frameworks through the ONNX file format. Okay, so I'm gonna start introducing ONNX. So ONNX is a cross-platform specification and file format for machine learning models, and it was designed to be a cross-platform from the get-go to allow many different frameworks like neural network packages and in general machine learning packages to exchange models with each other using this format. And you can see from all the partners that it is basically the cross-platform industry-widely supported format. Okay, so the Wolfram language can both import and export to the ONNX format. So I'm gonna quickly demonstrate a few simple import cases. So of course, importing is done with import. So this is an ONNX file we have in the installation layout of the Wolfram language, and we're getting a nice net graph out of it. Besides importing ONNX elements, some metadata can also be inspected and imported through these import properties. There are several of them, but the most relevant metadata are the operator set version and the IR version, which are the two versioning systems that ONNX use to represent and to version their specification. It is also possible to import the low-level contents of the ONNX file through the raw data property. So this is not really meant to be read by a human, but this is basically what this neural network looks like in the ONNX format. And it's also possible to only import the arrays through this array association property. Now, I'm going to quickly move to export, and then Maria is going to start demonstrating the pipelines. Okay, so nets are obviously exported via export, so we can define a net graph here and use export to export it to an ONNX file. It is usually possible to round trip, but it's not guaranteed to work in all cases. Like for simple cases like this, it's pretty much always guaranteed. And you can see we're getting the same networks back. And we can also set metadata. So there are three options here, and I'm setting them in export and checking that the settings are actually there. So this is enough for quick introduction. So we're gonna move on. I'm gonna stop sharing, and Maria will keep going to the bulk of the presentation.
Okay, hi, so my name is Maria Sarkisian, and today I'm going to present how you can basically convert the model from Mathematica to Keras, and then from Keras to ONNX and back to Mathematica. Okay. So we're going to start from the exporting the net from the Wolfram neural net from VLNets into ONNX, and then import it back into Keras. Okay, so for this task, I've chosen the ForkNet model. It's a segmentation model, which basically segments human brain into different anatomical tissues. For this model, it basically segments an image into white matter and the gray matter. That's very interesting architecture, basically a shared unit type encoder and then distinct decoders. Okay, we need to export a brain image into JPEG file to import it back into Python to see to run the model in Keras. Yeah, let's evaluate the model for the brain image, then export it to ONNX. As Matteo showed, it can be done by this function. And then let's try to import it back. And for this case, it's actually getting import. Yeah. And then move moving to the next slide.
You move the arrows.
Basically, you can run the Python code from Mathematica, and you need to define the external function to do that. I will evaluate the code, and during that also explain it. Okay, so basically to export a model, to import an ONNX model into Keras, you need to use the ONNX library and the ONNX load file. And then after that, of course, you need also to do the additional checker, which can be done by this way. And after that, it's importing to Keras model. It's very basic. You're just using the library of you're importing this from ONNX to Keras to ONNX to Keras, and then just inputting the ONNX basically the variable you get from the ONNX load, so the ONNX code type file, and giving a name to the input, and that's basically it. You can do the summary as usual in the Keras library. And what we're going to do is we're going to open the brain image in Python. Then we're going to basically set up an input for the Keras model, make the prediction, and then export the white matter and gray matter into an image and import it back to Mathematica. Yeah. So basically, to do that, what you need to do, since the Mathematica input image is when you encode the image into net encoder in Mathematica, it's giving you a range from 0 to 1. You need to also make sure that the imported image is from 0 to 1, so you're dividing by 255, and then also you're adding a new dimension for the badge, and for the first channel dimension for the image, and that's basically okay, so yeah, there's something stuck in at this point. Sorry, I can't evaluate it in white somehow. I've done the evaluation before, and basically I've written an image into JPEG file, and then as you can see, this is the image of the white matter and the gray matter on the brain image evaluated from Python, and this is the Mathematica output. Yeah, it's so it's also possible to export the model from Keras to ONNX, and then once you have the model in the ONNX format, you can import it back into Mathematica. And for this purpose, I've chosen Keras EfficientNet V0. Also, you have to take into consideration that if you want to export to ONNX from TensorFlow Keras, you can do it in two ways. One way is using this df1nx convert from Keras function, or otherwise you can convert your Keras model into safe model format in TensorFlow, and then use df1nx to convert the safe model format into ONNX. Yeah, but you have to make sure that you're using the right offset. So, for example, yeah, if you use offset 9, then you might the importer might fail in the importing the Keras model. And then also it's important to mention that our importer basically, if there are some operations that can be imported, the placeholders are getting placed into them, and then you can use the net surgery operators to basically replace them and get a runnable net. Yes, that's basically all from my side. I also let Tushita continue. Thanks.
Okay, so thank you, Maria. So since Maria has gone over the technical details of converting a model back and forth from one framework, what I would do is just continue in the same line. And I'll show examples from how you can do it from different other frameworks. So this one is from CoreML. So there is a tiny YOLO ML model, like CoreML model in their repository, and our goal was to get it from their repository to say net repository via ONNX. So from CoreML to ONNX, you use this package. It's called ONNX ML tools, and from ONNX you just directly import to Wolfram Language. So again, I will not be going into the details, but what I can say is you just use the package of ONNX ML tools, and this is what you do. So you load the core ML model, convert into ONNX, use the bunch of functions that's there in the core ML, like in the ONNX ML tools, and convert it. So one thing good to note is this size, and I just printed out the size of the network, and it's very similar to this. I've followed the steps written here. And then finally, it's not, again, it's not the end of this. So what you have to do is, once you have the ONNX, there are a lot of steps that goes on from getting ONNX file to finally getting it to the form here. Again, I'm not evaluating each of these examples because all of them are evaluatable in the slide. So you can just go ahead and evaluate them. Again, I'm not also sending the models because they are huge. If I had to package that and send it, it would be a lot. So go ahead, evaluate them. There are some closed cells which shows all the code that goes into from making a model, which is a single, which gives the backbone, to the final, say, tiny YOLO model, which looks like this. But there's a lot of steps involved from going, once you have the core ML model from ONNX to finally getting it to work. But I'll show you that it actually gives the correct answer. So here these are the labels. Again, there is a net evaluation function, which is hidden here. They are hidden, they are closed cells, but you can just go ahead and open them and see what they are. I just didn't want to just show all the code here. But essentially, you can try it on a test image and show that it actually parses, like it actually shows it gets the correct answer of cat and a dog. But that's again to get from core ML to ONN, to to our framework. Again, similarly, you can go from our framework to Core ML again via ONNX. So what you need to do is to export the model. So you export the model, the pre-trained model. The other thing that you need to make any classification is to export the classes as well. And this is how you get the classes, and then you get exported to your text file. So that's how you get the classes. So once you have gotten the classes, the other thing that you have to do is the second step. I think that is the exporting to ONNX is a single line function from Mathematica. But then again, you need to get it into ML model. So there are things that our encoders do. This is mean and variance correction. So you have to take into account those steps. Again, to export from ONNX to Core ML, you just use Core ML tools, and then you just use the proper functions which you want to use for converting it into Core ML. The thing that you wanted to do was mean correction. This is where you do the mean correction. Again, you see that these are converting the nodes. You will get the actual output that it's actually converting the nodes. So once you have converted the thing into Core ML, what you want to do is evaluate it in Core ML, and then finally evaluate the Core ML model and check it with your Wolfram language input. So this is basically the input that goes into evaluating that model. So what it is doing is just getting the image, doing the predictions. Here is the prediction, and then finally finding the top 3 probabilities from there, and then print it according to the probabilities and the class. Similarly, I just take the same image, evaluate it with our mobile net, and show the probabilities and the classes, and they match, which is, okay, this one is something which is not supposed to be there. But this is, again, the same probability from you see that they are the same, classes that it is there. So let's go ahead for the next one. So the final, there was Keras covered and Core ML covered. Now we have to cover PyTorch. So now you can convert a net from PyTorch to ONNX. This net was converted by Maria for our framework, for our neural net framework. So what you see here is just that she is splitting it into 2 parts to get it fully converted into our framework. So the first part gives the backbone, and the final part gives the weight of the final linear layer. But that's just it's a detail which we don't really need to go over, but this is sort of the process that you would go through when you are converting some model from, say, PyTorch to ONNX, and then finally you want to get it into Wolfram language. So here you just convert it from PyTorch to ONNX using Torch ONNX export. Now you have exported it. That's done. And then what you want to do is do necessary surgery, just like the tiny YOLO model that we had. It was not usable in that format that we got. That required more surgery. This requires lesser surgery. So here this is just this surgery form to make it this is just the usable form. It's not the form that you see in the repository. In the repository from this, we do she has done a lot of she's done a lot of regrouping of these of this graph to create in the final format which you see in the repository. So I'm just showing you the bare bones of how to make this usable. So getting from PyTorch to a final form that is usable. So this is a usable format where you can see that if you add the proper encoder and decoder, you can actually go ahead. So this is the final net form. So that's why fnet. But you can see that if I just had the fnet and actually get a data, like a video from our resource data, it actually gives me barbecuing. So this is a usable format, but this is not the format that we have in our repository. In our repository, it is it's more it's presented in a better way. So then again, the final step, that's the that's the sixth example, is to go from Wolfram Language to PyTorch. So again, via ONNX. And to do that, what we do is take the similar fashion. We take the pre-trained net, we take the classes, we export it. So the two things that we require are the pre-trained net and the classes, because we need to find what class it corresponds to. And then finally, once we have this, we have ONNX to PyTorch, and that is okay. That was a that needs to go here. But then we go from ONNX to PyTorch using this recently developed source ONNX to PyTorch. And then we just load the ONNX model, convert it, and then evaluate it in PyTorch. Again, we are just using transformations that are present, resize, center cropping, normalizing with standards. And then finally, we get we evaluate it. Similarly, we evaluate to get the three classes with highest probabilities. So these are the three classes with highest probabilities of a model that has been exported to PyTorch. And then finally, we have the same evaluated in Wolfram Language, and they kind of match. So that's the end of my part. I'll stop sharing to let Matteo speak about the future. So.
Okay, so this is going to be a quick conclusion about what are the future developments expected for ONNX import and export. So first of all, it's keep expanding the support for import and export. So what I mean by this is support of ONNX operators to import and support of Wolfram Language operators to export. And we expect that by 13.1, which is expected to come spring of next year, there should be all layers should be exportable. One other important point is to improve challenging cases for the importer, because unfortunately there are quite a lot of them right now, which mostly stems from the fact that our framework is a high-level framework, and other mainstream frameworks are lower level framework, which means that they are more detailed and they are more expressive, like while we are easier to use, but not as detailed. And so the main difficulty here arises for cases in which some of our layers have static parameters. So for example, the weights in a convolution layer, or the output shape in the reshape layer, that ONNX treats as extra layer inputs. So what I mean by this is when you create a convolution layer in the framework, it has arrays here, and they are statically included inside the layer. They're not an input to the layer. And same thing for the output dimensions of a reshape layer. So when these extra layer inputs in the ONNX model actually depend on the model inputs, which means that they change if the model input changes, we currently cannot import those models. And here I have created, using some internal functionality and a conveniently iconized ugly association, I have handcrafted one example like this, and you will see this error message when this happens. So sometimes this will need an actual upgrade on the flexibility of the framework itself to get fully addressed. But sometimes we can still improve this situation while keeping the framework as it is, and this is one of the areas where I want to focus for the next release. And then another important thing is allowing exporting to multiple operator set versions. So import basically doesn't have this problem anymore. So import can import from any ONNX operator set version. For export, the strategy we intended to adopt was to just only support the latest operator set version at every new Wolfram language release. But then we realized that sometimes other frameworks are slow to adopt the new version or actually stop supporting new versions entirely. And so it becomes important to have an option which can be used to export to a given operator set version. So yeah, this is what will be coming in the future. We got just a few minutes left, so you can ask questions if you want. And also, I'm gonna have my office hour event right after the end of this meeting. You can find it in the agenda, so if you have more questions, you can just go there. What's the difference between ONNX and MXNet? MXNet is a fully fledged neural network framework, like the framework you find in the Wolfram language. So it has, you can create networks in MXNet, you can run networks in MXNet, you can train, it has GPU support and all that kind of stuff. ONNX is nothing like that. ONNX is just a file format. So ONNX is not a package to run and train and build neural networks. ONNX is a file format to which you can export neural networks and from which you can import neural networks. Then there is a separate piece of software which is called ONNX Runtime, which is made by ONNX people. Not exactly made by ONNX people, but it's sort of like in the same ballpark, which is an actual framework, but it's a separate piece of software. Do you have a list of functions that cannot be exported to ONNX? Okay, so we have, you can check what is supported by evaluating this internal, this guy here. So this is what's supported right now. You have to, ONNX utilities must be loaded for this to work. So you have to import or export a model to ONNX before you can actually run this. Otherwise it won't give you anything, but this is where you check. Okay, so thanks everybody and enjoy the rest of the conference. Bye-bye.